I completed chapter 1 of FIS, Freidberg in-cell spins. In this last bit of chapter 1, I completed all the problems in section 1.6 and the ones in section 1.7 and the reading in section 1.7. I watched one more video in IIT Madras, but the content for these will lag this content. This content is almost like in here. And I'm going to take my time because this is a lot of time that I want to devote to making progress. But eventually, I think I'll get to all of these. So there you have it. There were 13 proofs that I completed in section 1.6 plus all the other problems. And then 6 proofs out of 7. So 6 out of 7 problems in section 1.7 were proofs. And this is a this video will go out December 4. And it's got 42 problems, out of which 19 are proofs. I'm up to 141 problems. I've attempted all of them so far, and 84 are proofs. And then in the case of section 1.6, the last problem is a callback to abstract algebra. I'll show it briefly when I get to it. And then all of section 1.7 is really uses something from topology. I'll mention briefly. So I've got a few props in here. Okay, so on to the book itself. It was all just doing all these problems. I had already read all of section 1.6, which was a very long read. This diagram is very important. I've used it for many of the problems. Just starting with a linearly independent set, then building it up to the size of a basis, and then anything beyond that can be a generating set. Yeah, so that was a long read and a lot of problems. Then in the case of, for section 1.6, the very last problem is talking about a quotient space, a quotient vector space, V over W. And I had to go through and learn a little bit about quotient spaces. Not sure I did the right thing here, but it's an attempt. And I'll come back to it when I do quotient groups in abstract algebra. Then in the case of section 1.7, it does a callback to these topological types, I don't know what to call them, that are called chains, nests, or towers, but really the term is really chain, which are collections of sets for each pair of sets A and B in the chain, and either A is in B or B is in A, so they're nested. There's all these nested sets. Okay, and then there was an example, a couple of theorems, and then all these problems. So I'll show my notebook, and this is almost an update. I would even call it like an update and a quarter, update and a half. But I didn't want to have a short video that closed out chapter 1 and have 5 videos. So, and luckily I had some holiday time, which allows me to do more hours than my regular week. And that always helps. So here are the problems for section 1.6. I did pretty well with the true and false. I only messed up one. And these are just basic linear independence problems that I've done before in Anton, except that now there's a new batch of problems that have to do with the interpolation theorem. Let me get the correct name. Yeah, the Lagrange interpolation theorem. Yeah, Lagrange interpolation formula. Lagrange interpolation formula. All right. So I think I got these problems correct, even though the book said that I got this problem wrong. I tested it and it does work. But okay, I'll take that as that. And then I got this one correct by the answer given in the book. Then I got these correct. The dimension n squared minus 1. I did a few examples and I could see that it was n squared minus 1 for the set of m by m matrices having trace equal to 0 as a subspace of all m by m matrices, square matrices. Yeah, and I got these dimensions correct for all these subspaces. Then in the case of the proofs, getting into the proofs, there is an answer. You know, the book points you to an answer. I'll put the link in the description. And Yeah, I could have done better. I was in the correct neighborhood, but I didn't use the text. I didn't. My proof is not as tight as it should have been, and I didn't go exactly all the places checking the span of beta correctly. So I gave myself a half. Yeah, I built the basis in a little bit of an incomplete fashion there. Then proof 21, of course, for which I don't have an answer, but I felt that I did okay. And 22, I also felt okay. And then for 23, 24, 26, I said n minus 1. It's n. I screwed up. Yeah, and this one I was off. I miswrote this matrix, and so I screwed it up. I should have paid more attention to the exact way to copy it correctly. Then in the case of problem 35, I went into a tangent, but I will resist. I came so close to actually saying, well, you know, how about I spent a couple of weeks reading through Rodman. I really like Rodman of all the abstract algebra first course books that I have, because it doesn't have, I don't want to use the word fluff, but all the historical things and all the applications that are in Hungerford and are in Galleon are out of this book. This book is just a bare bones, I'm going to get you there type of book. And I do plan to use it. Rodman also has an abstract algebra graduate book, so they kind of blend together. I don't know how many abstract algebra books I'm going to do. I have no idea if it's just going to be one pass or multiple passes for the first course. And I don't know if I'm even going to do the graduate one in this cycle. But Rodman is pretty good, and if I had done chapters 1 and 2, it'll get me to quotient groups and really understand that. But actually what really helped me was all these lectures by Socratica, which I will link in the description. And I got what I needed to understand what a quotient group is, and I came back to the problem, to 35, and I did the best I could. And I'm going to leave it at that. This could be wrong. That's why it's not, I don't have the diagonal slashes when I feel confident that I've done it correctly. But I did a good review of what cosets are. And now I understand what a quotient space is from the numbers mod 5. All these equivalence classes that are cosets form that quotient space, quotient subgroup. But I'm not sure that I translated it correctly to the problem at hand. Then I moved on to the callback for topology. And so when it comes to the Hausdorff maximal principle, of course, when you're going from finite sets to infinite sets, you can't use induction. Why? Because in induction, you're stepping through, and you're starting at 1, and then you're going all the way to n, and then you go to n plus 1. Of course, there's another induction where you can go n plus 2, n plus 3, n plus 4, or n minus 1, and n minus 2. You can go anywhere in there, but you're always stepping through. Well, the problem is infinity and infinity plus 1 are still infinity. So it's not going to help you. So you got to use something else. And so the book explains for infinite vector spaces how you can do a couple of theorems using the concept of a chain and the concept of the Hausdorff maximal principle. This section really turned this update into almost an update and a half, an update and a quarter, but I wanted to understand it. And of course, there's a footnote in the book that tells you where he got it, or where they got it, whoever one of the three did it, or all of them. It's from Kelly's General Topology book, which is a Dover book. And I've shown this book before. And sure enough, there's a whole section on the Hausdorff maximal principle, which is very good. I read this multiple times just to understand. Didn't go too much further into this book because, again, just like I don't want to start on Rodman, I don't want to start on topology. There will be a day, God willing, I do topology in gory detail, and the same with abstract algebra. But this is not that day. I need to move on with this book. And of course, our great Munkres has also deals with the maximum principle. He calls it the maximum principle, and he's got more content and describes how there are various people who came up with equivalence of this maximum principle. It's not unique to Hausdorff. It's just that Hausdorff is the one that Kelly used. But I did not go down those rabbit holes. But I did spend a fair amount of time on all the problems for this section. And it's all about building an infinite basis and proving that every vector space has a basis. That's what this section is all about. I felt very proud that the proof for problem number 5 is out. It's one of the links in the book. And I almost said there's no way that I could have proved this correctly because I said too much, and I'm never sure if I'm correct. But sure enough, when I read it, I was like, yep, that's what I said. Nice. Then I spent a fair amount of time on problem 6 and problem 7. It doesn't look it, but it actually took me a while to sort of like stack these infinite sets up. Not sure that the way I use this terminology is correct, and I don't have an answer for this, but I'm gonna say that I gave it a pretty good try. And that's the end of chapter 1.